octane. Have you heard of an octane rating at the pump? 85, 91, 97. So chapter 7 starts out with chemical reactions, and this is one of my favorite, and it means to combine with oxygen. So octane is a hydrocarbon. You've heard of an octagon. How many sides to an octagon? Right, so you've learned a little organic chemistry today. Now we have this fundamental law of chemistry that says matter can neither be created nor destroyed. So when I'm looking at this, presently I see one atom of carbon over here, and how many do I see here? I see 8. So this chemical equation might show how octane can be combusted with oxygen and become carbon dioxide and water, but it's not balanced. So we balance chemical equations by putting coefficients out in front of the chemical species. We never want to change subscripts, which sometimes students do, and that changes the identity of the substance. All right, and I see how many hydrogens over here? All right, so if there's 2, I gotta go 2 times something that equals 18. What would that be? So I've balanced carbon, I've balanced hydrogen, and I gave you a little guideline for balancing oxidation equations. Balancing chemical equations. And so the first element I chose was carbon, and then I chose hydrogen, and I left oxygen off to the very end because it's here by itself. So some of these guidelines, there's some little exceptions, but I tried to follow it. You can't always follow it. So now the question is, how many atoms of oxygen do I have? I have 2 over here. How many do I have over here? Well, there's 16 there, right? And there's 9 there. Yeah, I'll believe that 25. All right, so I need to write a coefficient in front of here. What times 2 equals 25? 12 and a half. All right, so we're just gonna start off with one of the hardest things, and that's when you're faced with this issue. And so here's a little help before you even get started. What's 1/2 times 2? It's 1. So I just got 1 oxygen there, so I can times it by anything that I need to. So I'm going to multiply by 25. And there, that took care of that problem. Now we have another rule that says we like to have whole number coefficients. Do I have a whole number coefficient there? No, so I need to get rid of that. And how do I do that? Yeah, I multiply by an integer that's going to get rid of that 2. The most obvious one would be a 2. So now I'm going to have 2 times this thing. That 2 cancels out, and I got 25 oxygens, 16 carbon dioxides, 18 waters. All right, now it's always good to check. So I might do something like this. Carbon on each side, I got 2 times 8 is what? 16, and I got 16 there. Let's go to hydrogen. 18 twice, 36. 18 twice, 36. Oxygen, 2 times 25. What do I got here? 32, 18, 50. So now we have a nice balanced equation. And in chapter 8, which I started preparing by accident last night because I wasn't paying attention, we figured out how to do calculations, like if I have a kilogram of octane, how much carbon dioxide will be produced. And these coefficients do the same thing we've seen before. This means 2 molecules of that, 25 molecules of O2, we get 16 molecules of CO2, 18 molecules of water, or we can just go from molecules to the mole and say 2 moles of octane require 25 moles of oxygen, and we get 18 moles of water. So any questions on balancing a combustion reaction? The hardest thing is when you have a odd number, and an odd number times an even number is always an even number. So a trick for a diatomic element, mainly oxygen, says put that in at first, and then you don't have to come up with 12.5 if your mind just doesn't go there. So we're gonna move on from combustion to this thing called, for right now, double displacement. I like to give it a special name. I don't know if that's spelled correctly. The iron hoedown. What's a hoedown? How many of you like to square dance? You switch partners. That's the main thing. But given this is Wyoming, you're probably into country line dancing, right? Did you hear about the cowboy that got totally addicted to country line dancing? Yeah, it was so bad he had to join a two-step program. Is to know your polyatomic ions, know your charges, and so a double displacement kind of takes this form of, and so in square dancing, A is going to get rid of X and hook up with what? Z, and B is going to get rid of Z and hook up with X there. Y'all like nomenclature? Let's just make this into a word equation. All right, so let's just use the English word and say, what's the name of the iron compound I form over here? Yeah, iron 3 hydroxide. All right, so that means over here I must have what? So who knows, that might be easier than writing the chemical formulas. So what is iron 3 hydroxide gonna look like? Now here's maybe how we wanna do it. We wanna keep our polyatomic ions as a whole, don't wanna take the oxygen away from the hydrogen, the O again away from the H. So how many hydroxides do we need? Notice there's a 3 there. Least common multiple between 3 and 1 is 3. 1 goes into 3 how many times? 3 times. So you got to put that 3 there. Then once you're done with that, you can say, all right, I know how that goes. And sodium nitrate, what's that look like? What's the charge on NO3? Must be -1 because I had 3 of them there for some reason. And we figured out we had iron 3. So one of the things we're going to learn in this chapter is solubility rules. A nitrate makes anything soluble. Most hydroxides are not soluble except for alkali metal hydroxides. So iron isn't a alkali metal, so this is not soluble, and we get a precipitate. So now the question is, we got the first part of guidelines for balancing chemical equations. What's the first guideline? Use correct formulas. If you make a formula that's impossible, that doesn't exist, it can make it so you can't balance the equation. So that's one thing to look at. All right, it says, generally you should select an element from the compound containing the most atoms and select an element present in the largest number of compounds if possible. And let's just skip down to 3. It says balance polyatomic ions as a single unit. So I don't want to try and balance oxygen. I don't want to try and balance hydrogen. And so I could just say, oh, I got 1 iron, I got 1 iron. Iron is balanced. How many nitrates do I have here? 3. So I'm going to have to put a 3 here. All right, how many hydroxides do I have? I have 3 over here. How many do I have over here? 1, and notice when I put this 3 here, that gave me 3. So I'm forced to put a 3 there. All right, now we could balance every element. On each side of the arrow, I have 1 iron, 1 iron. Maybe that's not too exciting. I have 3 sodiums, 3 sodiums. Typically, if we do polyatomic ions as a whole, everything's worked out. For fun, I'm gonna just forget about that. How many nitrogens do I have on each side? Right, I have 3 nitrogen atoms, 3 nitrogen atoms. How many oxygen atoms? Looks like I have 12 over there. 3 times 3 is 9. 3 more. How many hydrogen? So balancing polyatomic ions as a whole works out real nice because we can say how many hydroxides? I got 3. I got 3. How many nitrates? I got 3. And I got 3. So how do you feel about the ion hoedown? Let me dream up the most difficult double displacement I think I can think of. Calcium nitrate and ammonium phosphate. All right, what's the formula for calcium nitrate? So -1, +2, we're gonna need a 2 like that. These are all solutions. So you were all happy because you thought you were done with polyatomic ions. What's the formula for phosphate? What's the charge? All right, so now we look at that. We're gonna need our parentheses. Put a 3 there. All right, now the fun time, ion hoedown. How about calcium phosphate? What's that gonna look like? So I got a +2 and a -3. I say the least common multiple between 2 and 3 is 6. 2 goes into 6 how many times? 3. Then I need to get some parentheses out, and 3 goes into 6 twice. All right, then I'm gonna just clean things up and get rid of those charges. That's a good formula for calcium phosphate. What else gets formed? Absolutely. All right, so ammonium's +1, nitrates -1, so that's happy. So I'll keep on talking about solubility rules. Ammonium always renders something soluble, so does nitrate, so this is soluble. We'll find out that phosphates are typically insoluble unless it's hooked up with ammonium, which renders things soluble. Ammonium and alkali metals render most things soluble. So here we get a solid forms. We get a precipitate. So this should illustrate our guidelines nicely. Sometimes I tell students metal's a good place to start, perhaps. I got 3 calciums, 1 calcium. I'm gonna go ahead and put a 3 there. All right, how many nitrates do I have? 2 times 3 is 6. All right, I'm gonna have to put a 6 over here. Now notice I have 1 phosphate. Here I have 2 phosphates. And if I put a 2 here to fix up the phosphates, I'm gonna have a situation where it looks like everything is taking care of itself. 6 ammoniums, 6 ammoniums, 6 nitrates, 6 nitrates, 2 phosphates, 3 calcium. And we could check it element by element. Let's just do the hard ones. How many oxygens do I have over here? 2 times 3 is 6, plus 3 more, is that 18? And then I got 4 times 2 is 8. 8, 6 times 3, 18. Hydrogen. Oh, that's not too bad. We only have 1 source. 4 times 6 is what? 24. 4 times 3 is 12, plus 2 more is 24 there. Maybe I should have came over here. 24. So balancing polyatomic ions as a whole, or we could even use single displacement or single, let me fix this up. I should have chose a different one to start off with. Now water kind of looks like this when we think about all the electrons and the atoms. So to see this a little better, I'm gonna draw water like that. So what a single displacement does is you can always spot it because it'll be an element and then a compound. And what you form is, so let me just write this out. Element plus a compound always gives you an element plus a compound. And we typically have what we might call an active element. It's gonna kick off this element. So what's the name of the element? That's the name of the compound. Right, so the compound, we gotta incorporate sodium, and there's your clue. So this was kind of a question on the last exam. What's the formula for elemental hydrogen? Is it just H? It's a diatomic element, exactly. It's one of those 7. And I say it kind of, you can imagine a 7 on the periodic table. See how that makes a 7? 1, 2, 3, 4, 5, 6, 7. Is this thing balanced? Look, hydrogen's balanced. Guidelines say don't do, they say do hydrogen and oxygen last. But, so that means do sodium. 1 sodium, 1 sodium. Yay. 1 oxygen, yay. 2 hydrogens, and 1 and 2 make 3. So I'm gonna have to start writing numbers somewhere. Maybe we don't know. The easiest thing is I got an even number here. How do I even this up? If I just get 1 more there, now I have 4 hydrogen. I have 2 oxygens. 2 oxygen. All right, hey, I got I now have 4 hydrogens, 2 oxygens, 1 sodium, 1 sodium. Most hydroxides are insoluble, unless it's this rule 1 exception, alkali metal or the ammonium cation. That's a horrible L. Let me fix that up. It's perfect. It wasn't before. I was talking and I wasn't thinking. Thank you, Emma. So what have we covered? Combustion, double displacement, single displacement. We have time for one more? Or you want to leave? Another single displacement. We got copper and silver nitrate. Now, I'm going to just give you a hint. Here it's metallic copper. Here it's copper 2. It also turns out these are oxidation reduction reactions, redox reaction. All right, well, what's the single element? 2 silvers, 2 nitrates, 1 copper, 1 copper. We'd have to name this silver nitrate. Now this is just copper, elemental copper. All right, that ought to do it.